In this video, I'm going to review one very recent article published in the journal, a very prestigious Journal of Thermal Analysis and Calorimetry. And this article is published in 2024, a very recent article. The journal is very good and they picked a very good problem, but there are some issues in this paper, some technical issues, or we will talk about that, and you will also learn from that. Actually, what happened is while working on this problem, solving this for MATLAB, I came across some technical things which is not suitable for the bvp4c or any numerical method. We will talk about that, and you will also learn from it. So this paper actually discusses dusty fluid cross stretching sheet. There is one issue with this title is there is no nanoparticle radius. In fact, to my knowledge, while reading this paper, I can't find nanoparticle radius, and we will also talk about that as well. These are the governing equations. As you know that for dusty phase fluid particle, you may have two kinds of equations. One is for fluid or nanofluid, and another one is for dusty phase fluid. So in the first phase, in the first part, we have continuity equation. U1, U2 are the velocities in x and y direction. The second one is momentum equation, and you may find some of the terms from the particle as well, and MHD, so on, and energy equation is there. And now the second part of these equations are dust phase equations, and these are for the particle, dust phase particle. That's why there is P written in subscript of these variables, under these variables. The problem is very good, no doubt about that. And we have boundary conditions over here. And the issue that I was talking about is regarding these boundary conditions. You may see that, for example, in these PDEs, or let me just go to ODs first, and we will talk about that, the boundary conditions. We have similarity transformations. We have these similarity transformation for U1, U2, eta, theta 1, and theta 2. But probably I have missed some U1P and U2P. That should also be here, I guess, which I probably missed it while typing over here. So while downloading the paper, you can see those similarity transformations yourself. These are the ODs. From PDEs to ODs, you use these similarity transformation to convert PDEs into ODs. What we see that the first ODE has an order of 3, since F has third order ODE, theta 1 is second order ODE, G is second order ODE, and theta 2 has first order. So the total order of these ODs are third 3 to 5 to 7, then 8. So it means that we need 8 boundary conditions. Now look at the boundary conditions they provided in the paper. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9. It means that they have put it, I guess, 9 boundary condition. They have uh, written 9 boundary conditions in the paper, which is incorrect. The order of the ODEs, order of your differential equation, must equal to the order of the boundary condition. Number of boundary conditions should be equal. Then you can solve this problem. And that was the big issue in this paper. The problem is good. Probably the journal is good. Problem picking is very good. That's why it is published in a very good journal. But probably they have missed out, or they did not carefully look at the boundary conditions. Now, if you are reviewing this article, then you probably would not know, you probably would work on hit and trial. And that was an issue with me as well. While solving this, I have to consider from hit and trial which boundary condition should I consider and which boundary condition should I remove from the bvp4c code. So as you know, so let's move to numerical method. So as you know from bvp4c code, we first convert ODEs into a system of first order ODEs. And you can see that there are how many variables you define first: y1, y2, y3, y4, y5, y6, y7, and y8. There are 8 variables. Since the problem is the third, the last one, not third, the last one is theta 2, which has order 1. So it means that we need 8 variables. If I am wrong, then you can comment in the comment section and correct me if I am wrong somewhere. To my understanding, there is some issue in the boundary conditions. So these are the system of first order. You can pause the video and write down all the system of first order differential equation. These are the system of first order differential equation. I might have some typing thing, but 100% I'm sure that this is correct 100% over here. These are the boundary conditions, and as you can see that for implementing in MATLAB, we need residual of the boundary condition. So we have y01, which 0 shows that variable at left hand point, which is 0, and ynf shows that we have boundary condition at right hand point, which is infinity. And as you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 boundary conditions, and we have to omit one boundary condition, so that number of system of first order ODEs must be equal to number of boundary conditions. These are the parameters, and there is another issue with this. You can see the parameters M, Prandtl, C1, C2, so on, and other parameters as well. But the image that I copied from their paper is given over here, and there is no dp. That's probably there in the title. They are talking about nanoparticle radius. To me, it looks like this, but there is no dp defined. Oh, there is a dp over here. I see. There is a dp over here in this term, C1 or something. Probably I have written it wrongly. But dp and other variables are not defined properly. Okay. So when you put dp over here, then you have to calculate C1 and other things, something like that. So this is not a big problem. dp is there. So in the title is also fine. title is also fine. Maybe they are calling it nanoparticle radius. But this is the issue, that they have one additional boundary condition, which we have to pick and choose which boundary condition should we take so that we can reproduce their result. Okay, the problem is very good. Mathematical modeling is good. You can probably extend that for your research. Okay, let me just go to the bvp4c code, which I will provide you in the description. This is the bvp4c code. I shared it many times on my channel. So that's how you define parameter first. This is the standard thing. Then we have plot. Then we have temp1 to temp4 temporary variables. These are the system of first order ODE. Then we have residual of boundary condition. Okay, so I just run it. How we run it? When you run it, you will get the some graph. So probably you will not get the correct graph. I don't know how they created it. So I don't know how to generate these graph, since the boundary condition is not correct.